This is a video from section 1.4 in a linear algebra class. Let A equal the matrix ABCD. If AD minus BC doesn't equal 0, then A is invertible and A inverse is 1 over AD minus BC times the matrix D negative B negative C A. And with that, let's take a look at problem 5. In problem 5, we have A equaling the matrix 2, negative 3, 4, 4. And I want A inverse. Okay, so A inverse is 1 over AD, which is 2 times 4, minus BC, which is negative 3 times 4, times the matrix 4, 3, negative 4, 2. So if you notice, this 4 is D, this 2 is A. This 3 up here is the opposite of negative 3, which is 3. And this negative 4 in the lower left is the opposite of 4. So notice we changed the sign of this 4 here to make negative 4. We changed the sign of this negative 3 to make 3. And then notice how here's D, here's A. Okay? And so this is 1 over 20 times the matrix 4, 3, negative 4, 2. And then if we simplify, we get the matrix 1/5, 3/20, negative 1/5, 1/10. So I took 1/20 and multiplied it by every entry within the 2 by 2 matrix. And that's how we do number 5. So let's take a look at problem number 6. Suppose B is the matrix 3, 1, 5, 2. Okay? And I want B inverse. Well, B inverse is 1 over 3 times 2 minus 1 times 5, right? Times the matrix 2, negative 1, negative 5, 3. But 3 times 2 minus 1 times 5 is just 1. And so when we simplify this, we get the matrix 2, negative 1, negative 5, 3. And that's how we do problem 6. Let's take a look at problem number 7. Suppose 7, we have the following. C is the matrix 2, 0, 0, 3. So C inverse, right? And if it helps, that's a capital C, okay? So we can exaggerate that C a little bit if we need to. Now, C inverse is 1 over AD minus BC, which is 1 over 6, times the matrix 3, 0, 0, 2. And so when we simplify this, C inverse is the matrix 1/2, 0, 0, 1/3. And C is a diagonal matrix, which means essentially we have entries along the main diagonal. They could be 0, they don't have to be 0, but the entries off the main diagonal must all be 0. So you notice the entries along the main diagonal of C are 2 and 3, right? The entries off the main diagonal are zeros. And so it's very straightforward to calculate C inverse. We applied the formula for this problem, but you might notice, and it's not a coincidence, the reciprocal of 2 is 1/2, right? And that's the entry in the upper left-hand corner of C inverse. The reciprocal of 3 is 1/3, and that's the entry in the lower right-hand corner of C inverse. So it makes it really, really nice to find an inverse. If we take a look at number 8, D is the matrix 6, 4, negative 2, negative 1. D inverse is 1 over AD minus BC, which is 6 times negative 1 minus 4 times negative 2. So in other words, we get 1 over 6 times negative 1 minus 4 times negative 2 times the matrix negative 1, negative 4, 2, 6. So the first entry here is lowercase d. That's this entry, right? The second entry is the opposite of b, right? Remember, this is b. This is negative b. This entry is c. This entry is negative c. And then this entry is a. So when we go to simplify this, we get 1/2 times the matrix, negative 1, negative 4, 2, 6. And then we go a little further. This is the matrix, negative 1/2, negative 2, 1, 3. And that's how we do number 8. Let's take a look at number 10. Now, on number 10, we have the following. I'll just call it A. Let A equal the matrix. And we have cosine theta, sine theta, negative sine theta, and then this one's cosine theta. And I want to find A inverse. So this is 1 over cosine squared theta minus sine theta times negative sine theta, right? So it's 1 over AD minus BC times the matrix. Now, we have cosine theta, right? So remember, this entry is A, this entry is D, right? And so here, yes, they're the same entry, but I'm calling that entry D and this entry A. Now, if we look at the entries along the other diagonal, we get negative sine theta for the top right, and then sine theta over here for the lower left. So negative sine theta for the top right, sine theta for the lower left. So here we get 1 over cosine squared theta plus sine squared theta, right? A negative times a negative is a positive, times the matrix cosine theta, negative sine theta, sine theta, cosine theta. But what is cosine squared theta plus sine squared theta? Well, that's 1. And so here I get the matrix cosine theta, negative sine theta, sine theta, cosine theta. And that's how we find the inverse. Now, I want to show you number 15. 15 is a great question. So suppose I do the following. Given the inverse of 7a equals the matrix negative 3, 7, 1, negative 2. Okay, so I'm given this. I want to find A. Now, recall, the inverse of A inverse is equal to A, right? So, if I take the inverse of 7A and then take the inverse of that, are we in agreement that this is equal to 7A? That's the key to this problem. Okay? So we're going to do that first. Now, let's rewrite this. The inverse of 7A is the matrix. Let's remind ourselves. So this is -3, 7, 1, -2. Okay? And I want to find 7A. But that's the inverse of the matrix -3, 7, 1, -2. And applying that formula, we get 1 over 6 minus 7, right? -3 times -2 is positive 6. 1 times 7 is 7. And then I'm going to write -2, -7, -1, -3. Okay? But isn't 6 minus 7 -1? And so essentially I can take every entry in matrix 7A and multiply by -1. When I do that, I get the matrix 2, 7, 1, 3. Just like this. So let's talk about this. So 7A is the matrix. And then we get 2, 7, 1, 3. But are we in agreement that A is then the matrix 2 sevenths, 1, 1 seventh, 3 sevenths? And that's how we do problem number 15. Let's take a look at problem 16. 16's good. Suppose we're given that the inverse of 5A transpose, okay, is the matrix -3, -1, 5, 2. Well, what I would do is I would look for 5A transpose first. But isn't that the inverse of the matrix -3, -1, 5, 2? Okay? And so this is 1 over -6 minus -5 times the matrix. Now I'm going to put 2, -3. So I swap the entries along the main diagonal of 5A transpose. And then along the other diagonal, right, I change the signs of the entries. So I'm going to put a 1 up here and a -5 down there. Okay? And so, therefore, 5A transpose is 1 over -1. That's what -6 minus a -5 is, times the matrix 2, 1, right? That's the first row. -5, -3 is the second row. And so we get -2, -1, 5, 3. And so that is indeed 5A transpose. Now what we can do is solve for A transpose. When I solve for A transpose, I get negative 2/5, negative 1/5, 1, 3/5. Are we in agreement on how to get A? To get A, the entries along the row of A transpose become the entries along the column of A. So in other words, I'm going to put negative 2/5, negative 1/5 in the first column of A, and then 1 3/5 in the first, or in the second, that is, column of A. So I solved for A transpose, and then from A transpose, I was able to get A. That's how I do number 16. Let's take a look at number 18. So if A inverse is the matrix 2, negative 1, 3, 5, recall, the inverse of A inverse equals A, okay? And so A is 1 over 2 times 5 minus negative 1 times 3 times the matrix. And then I'm going to put 5, 1, right? And then that's the first row. In the second row, I put negative 3, 2. From here, this is 1/13 times the matrix, 5, 1, negative 3, 2. And so if I simplify a little bit, I get A equals the matrix 5/13, 1/13, negative 3/13, 2/13. And that's how we do problem number 18. That's probably a good stopping point for this video. And so this is a video from section 1.4. And then in this video, we did problems 5, 6, 7, 8, 10, 15, 16, and 18. Okay, thank you.